I'm excited to be here and appreciate the time that you've taken to join this webinar. I'm joined actually by Dr. Scott Bergeson, who's a professor in the Department of Physics and Astronomy at Brigham Young University here in Utah. And he, along with his co-worker, Justin Petrus, were the architects, or in some ways the inventors, of the S2 and the S3 biophotonic scanners. So we're really happy to have him here today. Dr. Bergeson holds the patent for Raman instrument for measuring weak signals in the presence of strong background fluorescence, which is the method used by the scanner to measure carotenoids. And one of the reasons why we invited him here today, because we're going to be talking a little bit about how difficult it is to measure weak signals in strong background fluorescence. Dr. Bergeson's research, in case you're interested, is in atomic physics, including laser cooling and trapping, ultra-cold plasmas and strongly coupled Coulomb systems, and spectroscopy. I hope you know what that is, because I'm not sure what some of it is. And I'm Mark Bartlett. I think I know many of you. I recognize some names here on the call-in. I've been with this company, Nu Skin, for nearly 20 years now. Before I was at Nu Skin, I was at the National Cancer Institute, where I was looking at the interaction of cells, especially in the context of cancer and autoimmune disease. So my background is immunology. Some of you may detect an accent. I'm from Australia, where I studied my PhD at the Australian National University in Australia. We're excited about the progress. We are excited about this latest edition of the scanner and the progress that it's taking. But we wanted to take this opportunity to provide a little extra education, a sort of a technical update, if you will, beneficial to you. So let's begin. Talk a little bit about the evolution of the scanner. This will be very familiar to you, so we won't spend a lot of time on it, but you may recall that the first scanner, which we came across at the University of Utah, Department of Physics. I don't know if you can tell us a little bit more about this,
sure,
Dr. Bergeson.
This early scanner used a research grade machine, so this was a large argon ion laser, which was coupled to a state-of-the-art scientific CCD spectrophotometer array. And it really indicates how most of the people who use Raman spectroscopy are people who are working on PhDs in physics or chemistry.
Right, so this is sort of a greenhouse device, not something that you'd take into your living room, to be sure, right? An argon laser that was several feet long. Whenever you wanted to make a reading, you had to get a dewar of liquid nitrogen, pour it in to cool the laser. So that's something that we became hugely interested in because of what it could measure and the overlap with the work that we were doing. So of course the S1 scanner was born after no small effort and a huge amount of money. And this device was revolutionary, really a disruptive technology, but it had some weaknesses, but we were certainly willing to put up with that considering it was the first device, right? A 30-minute warm-up and a 15-minute calibration meant that, you know, it was about an hour before you were able to use this in the field. But still portable, and this is where people first learned the importance of carotenoids in the skin and its relevance to our health. Of course, the next evolution was really almost a revolution, really, with the S2 scanner. Tell us a little bit about this, Dr. Bergeson.
So in the S2 scanner, our goal was to make a Raman spectrometer that would be even smaller and be more robust, less sensitive to temperature variations, something that would be easier to calibrate, and we worked to incorporate into this internal calibration standard so that you could eventually get rid of all the pCal.
Yeah, and that was a huge burden that was dropped off individuals that wanted to, again, take this into their living rooms or wherever to help people measure their carotenoids. So this was a really nice addition. But still, this S2 scanner was connected to a computer. There were wires and you know, a nice quick warm-up, and certainly a lot more robust, as we'll talk about later. But still, there was a demand for something that was smaller, more mobile, and that was when the S3 was born. And this took quite a bit of development. But again, the goals were to have something that had a faster scan, a smaller device that was lighter, something that was more portable, preferably without all the wires, and something that would actually even have on its own interface the scan on the device. There was a sense, I think, early with the S2 that somehow the computer itself was generating the answers, and maybe it was even a random number generator. So actually having the device with, you don't see it on this picture here, but with the readout on the top of the device, gave people more of a sense that the device itself was the smart technology, which it really always has been. This is portable and it's digital. And again, comparing the times, a 3-minute scan now brought down to 30 seconds. So this has really helped to make it easier to scan more people more efficiently. The weight, this slide just shows the difference in weight. We've gone from 7.5 kilograms plus a computer and everything else down to 1.7 kilograms. And I think what's really the neatest and the slickest is that we have now an internal battery that's good for about 500 scans. We have wireless connectivity, and that's to the marvelous iPad with an app in there that's being used to run this scanner wirelessly. So this makes it very slick, really brings us up to the 21st century, sort of like an iPhone type thing. So I think everyone agrees that this is a huge step forward in evolution of the scanner. There are some other sort of housekeeping type things. Digital scans are now an option, right? So this eliminates the need for physical cards. I feel that that's something that the distributors have demanded, and we were able to deliver. So we can still use physical scan cards as an option, but this idea of the digital scan makes it really nice and easy. Let's talk a little bit about then the manufacturing of the scanner. You know, that's sort of what we deal with. We have to build these things, and we have to build them to a good standard. So we use, obviously there are standards that we can adhere to, and what we've chosen to follow is the CSA, the Canadian Standards Association, which dictates good manufacturing practices, cleanliness and record keeping, and this is an organization that audits our manufacturing plant every quarter to make sure that we are following best practices. We calibrate the scanner using the same methods basically as the S2. So this involves several quality assurance technicians checking as we go, just as a distributor would basically. Once the product is manufactured, then we basically have pretend distributors as our quality assurance agents that inspect each scanner, use it just as a distributor would, and make sure that everything's working, that it's connecting properly, and also that it's calibrated correctly. Now, we do appreciate that after shipping, sometimes small adjustments are necessary. Usually we can do that remotely, and we can certainly do quality checking remotely. All right, your market also performs quality assurance checks before they go out to you. So the same criteria as the scanner plant is being repeated in the European market to make sure that the scanners are working correctly. And scanners that fail before they even get to you are sent to the scanner plant for rework.